All right, I think we might as well get started. If people come in, then people come in. Cool, so today we're going to talk about debugging and profiling. The reason for this is because as great as computers are in terms of being a tool we can make use to do almost anything, they also have a tendency to do only exactly what we told them, which is not necessarily what we intended for them to do. And hence the need for debugging, to sort of try to explore that delta between what we wanted the computer to do and what it actually ended up doing as a result of what we told it. There's sort of a quote from one of the famous people behind the C programming language, Brian Kernighan, who said the most effective debugging tool is still careful thought coupled with judiciously placed print statements. And this, I think, remains true for me as well. A lot of the debugging that I end up doing ends up just being print debugging, where print debugging really just means in your code, stick a bunch of print statements that print out information that helps you think through what the program is doing, and where you're thinking about what it ought to be doing doesn't match what it turns out to be doing. The print debugging is sort of seen as a kind of crude cudgel, if you will, but it actually works really well for a lot of cases. The biggest problem with print debugging is you sort of start from scratch each time. The program runs, and then you need to start to narrow down where the origin of the problem might be. And so this is where we get things like logging instead. Logging is really just a more principled use of print statements, where those print statements get to stay in your code over time. So rather than just being things that you stick in there for your particular debugging sessions, you have these longer-lived logging statements that log things that you're expecting to be useful almost any time you want to debug your software, be that because it broke, or because you want to understand its performance, or you want to implement a feature, whatever it might be. So in general, in larger code bases, and especially in production code bases, you'll find a lot of logging. This can either be unstructured logging. So unstructured logging tends to be things like just printing out text saying what the program is doing, or it can be structured logging. This could be things like metrics. It can also even be JSON blobs that gets logged over time so that you can more easily extract information from those logs as the program runs. So if you'll remember in the first lecture where we talked about a bunch of the shell tools you have available, it's often useful to be able to use the shell tools to parse and extract information from your logs. And if your logs are at least semi-structured, that helps making it easier to use the tools to extract that information after the fact. There are a bunch of conventions around logging. Like usually most log entries are going to have at the very least a logging level. So the logging level will be things like trace, debug, info, warn, error, critical, to indicate how important this logging level is. And most applications or libraries then have a mechanism for saying, I only want to output log things that are of at least this level. So when you run your code base in production, for example, you might turn off the trace and debug logging and only keep info level or above, for example, or maybe only warnings and above, so that you don't spam the output all the time. Whilst when you're debugging, you might enable more verbose logging to give you more details about what the system is doing. And usually, like the more sophisticated logging software or frameworks in many languages allow you to specify this per module, per file, to say, this part of my application I want to log with trace debugging or trace logs, and the rest of the application is going to be warn only, because that's the part I want to dig into. Usually, logging statements are things that you put in proactively. So as you write the code, you go, this would probably be useful to log. But one of the things that sort of connects print debugging and logging is that when you do print debugging, in a way what you're saying by sticking a print statement in there is saying, this ought to have been logged so that I wouldn't have to print out this information now. So usually a good sort of second step after you stick a bunch of print statements in there is to then turn them into log statements so that the next time around, your program, like when your program just runs normally, you get more information out of it and you're less likely to have to go through the whole change and recompile cycle in order to figure out the flow of the program. You'll also find that there are a lot of third-party programs you interface with where maybe you don't have the code or you don't know how to build it, or at least it would be annoying to do so. A lot of third-party applications already have logging built in, and the question is just to figure out how to access those logs. For a lot of the command line tools, you can pass -v or --verbose to give more output from that program, and you can often stack these flags. So you can pass like -v or -vv to say be even more verbose, and this can give you insights into what the program is doing and hopefully why it doesn't behave the way you expected. For system services, you can often introspect those services on whatever operating system you might be on. For example, on Linux, this is usually through the journalctl tool, which lets you say, give me the logs, like give me all of the outputs from this particular application that's running in the background, like the SSH daemon, for example, for servicing remote connections. But when you're writing programs, the reality is that print debugging only takes you so far. Usually, you start to get into a space where either it gets really annoying to recompile and redeploy your program each time, or sometimes it's just like you don't really know exactly what to log. You kind of need to observe the program as it executes and decide what information to extract. And this is when you use debuggers. There are a bunch of different types of debuggers, but some of the most common ones are GDB and LLDB, that are both essentially the same program. They're not the same program. They have very similar interfaces, very similar interaction models, where they attach to a currently running process and then allow you to control that process's execution. So you can do things like stop when you reach this line in the code, introspect memory while the program is paused, resume the program until the current function finishes. Those kinds of commands. We'll see an example of that in a second. These are general purpose debuggers. So they work with basically any program, but they tend to prefer programs that have been compiled, native programs. Things written in C, C++, Rust, couple of other languages, like in general, the things that produce like binaries that go on your file system. If you have a more runtime focused language like Python, JavaScript, Java falls into this category as well, then you Go to an extent as well. You will usually want to use a language-specific debugger. So for example, for Python, there's a tool called PDB, which is very similar, as its name implies, to GDB, but it's specific to Python programs. But it lets you interface with the program in the same way, to say, stop when you hit this thing, watch, like notify me when this variable changes, allow me to introspect the state of the program, and so on. Now, what I'll show you in a second is the interface to GDB, but first I want to talk about something called reverse debugging or record-replay debugging. So when you do debugging using a debugger, it really just executes your program normally. It starts the program at the top, and it runs the program until it exits, or forever if it never exits. And then as it runs, you get to stop it and resume it. Those are your two primary mechanisms of control. What is sometimes frustrating about this is sometimes you let your program run, and you discover that you've hit a bug of some kind. But what you really want to do is now go backwards to figure out how you arrived at that bug. Like, what was the order of operations that caused this number to be 4 instead of 5, or this Boolean to be true instead of false? But by that time, your program is already executed past where the real bug was, and you're just stuck at the point where the bug manifested, which is often not what you're after. So there's this thing called reverse debugging that is really useful to debug these kinds of problems. There exist tools for this. One of the primary ones for Linux is called RR, for record replay. It actually has the exact same interface as GDB. All the commands are the same. The only difference is that RR will record everything your program does. All of its interactions with the operating system, with memory, everything gets recorded and written down so that the program can be executed in reverse order. So when you start a program with RR, it runs your program start to finish and records everything that happens. This allows you to, when you hit a particular breakpoint, so when you told the program stop when you hit this line, for example, you can do a reverse step. So instead of stepping to the next line of code, you can say, undo the current line of code and pretend like we're in the world where the program is one line higher up. And that let me introspect the state. This can be very, very powerful for tracking down tricky bugs. Before I show you RR, I also want to mention there's a class of bugs called Heisen bugs, so named after the uncertainty principle, where the Heisen bugs are bugs that when you try to observe them, they are not there. You will most commonly run into this when you do print debugging. So print debugging will slow down your program, because now your program has to like stop and write a bunch of characters out to your terminal and then go back to running the program. And that small delay can sometimes cause your program to behave differently than if it got to run faster. This happens especially for concurrent programs where a bug might manifest because one thread was faster than the other. Well, if you put print statements in the faster thread, then that thread now got faster, and then maybe it doesn't observe the bug in the first place. The same thing can happen with these debuggers, because they change the way the programs are executed. This is especially true for RR, because when RR runs, it has to record the entire program's execution. And one of the ways it does that is it uses a deterministic scheduler. So it runs all the threads in a very specific order, so that it gets to capture all of their information and so that you can reverse step. But it could be that your bug does not manifest when the threads run in that particular order. So you can have a program that when you run it normally, crashes or hits some bug, and when you try to record it with RR, it does not crash. The bug does not manifest. And this is the lovely world of debugging, where sometimes you have to like pick and choose the tool, not just based on what abilities it gives you, but also whether you can even reproduce the problem there. So let's take a look at what RR looks like. So with RR, I have a program, corruption.c. This program is actually in the exercises, which is why I'll remove this comment. And here we have a struct that has a string. This is a C program. It has a string that's a name. It has an ID and a balance. And we have a bunch of accounts. We have Alice, Bob, and Charlie. Each of them have some amount of money in that account. We have a function that lets you update the name of an account. We have a function that prints out the balance of all the accounts. And what we do is we print out the initial state of all the accounts. We make some changes to some of the balances. We update the name of one of the accounts. And then afterwards, we print out the accounts again. And in this particular case, I've already narrowed down the bug a little bit. So I've observed that when I do the print accounts here, after updating the balances and the name, something weird happens. In particular, the ID of one of the accounts changes. Like when we look at the setup of the accounts, account 0 has ID 1, account 1 has ID 2, and account 2 has ID 3. But at the end here, I observe that account 0 no longer has ID 1. But none of the code above here changed any of the IDs. The only thing it did was change the balance field and the name field. So why is the ID wrong? Well, let's see what happens. So what I'm going to do is I'm going to compile this program. The -G here is include debugging symbols. This is basically like include the names of variables, the names of functions, and so on in the program, so that when we later open it in a debugger, it doesn't just see like memory addresses and locations and binary data, but it also has information about this part of the binary file. These assembly instructions are actually this function in your source code. It sort of preserves that mapping. So that's what the -G does. And we say corruption.c, and -O is where do you want me to put the compiled file. I'll call it corruption. When I run corruption, you'll see that the initial state here is as we would expect, but after the operation, the accounts afterwards, you see that account 0 has the correct name, Alexandria, but the ID is something completely different. And we need to figure out why that is. So what we're going to do is we are going to do RR record the execution of corruption. What this will do is it will run the program, record all the stuff that it does, and then stick it in a file on disk. So if I ls here, actually, sorry, it sticks it in a hidden directory, so we can't see the file here, but it records it on disk. When I then do RR replay, what this will do is it will load that file, and then it will resume the session that runs this program. I could, just to show you what the GDB version of this looks like. So if I do gdb./corruption instead, and I do run, then it runs the program and it leaves me at the end of the program where it exited. So this is what it looks like with GDB. There's no record or replay. It just runs the program and leaves me in this prompt where I can do things. And you'll notice that if I do RR replay, it looks almost the same. It might be hard to sort of squint at here, but it still prints out that we're actually in GDB when I run RR replay. And it also shows us that there is like reading some debug symbols, and if I type run here, start the program from the beginning, it runs start to finish, and says program stopped. And I can do continue, and then it runs the program, and you'll see it prints the same thing as if I ran the program normally. Just like in GDB, when I ran it, it ran the program to completion and says the program is executed. If the program crashed for some reason, then it would stop where the crash was. But in this case, my program doesn't crash. It just like prints a message saying this ID looks weird. So let's figure out why do we get inside of this if condition in the first place. So what we'll do, we can type list here, and list will print out the source code as GDB sees it, or as RR sees it. And so I can even do list to list more lines of code. And in this case, what I want to do is I want to set a breakpoint down here on this if. A breakpoint is something where you say, when execution hits this line or this part of the program binary, then stop executing and put me in control. So in this case, I'm going to say, put a breakpoint at line 52. And then I'm going to say run. I want to start the program from the beginning again, because it just finished. And then I say, R for run, and I'm going to type C for continue. Because when you type R, it just starts the program at the beginning, but it does not resume it yet, to allow you to set breakpoints and such. So now the program counter, the thing that points at where in the binary we are, points at the start of the main function. When I type continue, we'll start executing main, and it will execute all the way down to the first breakpoint it hits. So in this case, you'll see it ran the initial print, and then it ran the print after the balance change operations. And then it says we're now at breakpoint 1 in main at corruption.c, line 52. This is the line that I'm about to execute. And now what I can do here is I can start to introspect the program state. So for example, I can do P for print. I could also type print, but P is shorter. And I can say I want to print accounts0.id. So in this scope, I'm allowed to access any local variables that exist in this function. I basically get to inject lines of code that get executed immediately and print out what they are. There are a bunch of ways you can modify this. Like I could say print this in hex, or I can like explore structs and arrays in this way. There's a bunch of things. You can even call functions from in here. So this is a pretty rich environment. We won't talk about all of it. But in this particular case, what I actually want to see is I want to know, when did that ID change? When did it change from 1 to this weird number? In GDB, I would kind of be out of luck, because at this point, it's already been corrupted, and all I can do is continue. So all I can do is go to the program end. So I would need to like set breakpoints earlier and earlier and earlier in the code and run it again and again and again and see, oh, when I set the breakpoint here, it's not corrupted yet. And I would sort of have to search for myself. With RR, I can do something pretty cool. I can say watch account0.id. This is also something you can do in GDB. You can say watch this expression and break whenever the value of that expression changes. I can do the same thing in RR. Accounts. But now what I can do is I can do reverse continue. So what this will do is, instead of executing down, like continuing execution in main, it will undo the executions of lines in main until this watch point is hit. So until that value changes. And you see here, when I reverse continued, it says, oh, we hit a hardware watch point for this expression. The old value is this, and the new value is 1. And remember, this is reverse continuing, so the new value is the older one, and the old value is the newer one, right? Because we're executing from future time. And so here, this is where that value changes. And so the question is, where is this? Well, you can type backtrace, or for short, BT. And BT will give you a stack trace, a backtrace, that shows you the sequence of functions that you're currently in. So it will show you the whole call stack of functions all the way down to the current line that's being executed in the current scope. So in this case, we see the function that actually did the editing of ID is this string copy AVX2. So this is like in the C library somewhere. The function that called that, though, was update name. And then you see down here the arguments to that function in the problematic case. So you see that when we give the new name of Alexandria, we call update name, the string copy executes, and that for some reason ends up changing the ID. Well, that's interesting. So that immediately tells us this is the function that is the problem. So if we now do list update name, and we look at this function, well, the update name function, all it does is it does a string copy. So let's go, let's exit out of this, by typing quit, you exit out, and we say, it says here that the program is still executing, and I go, that's fine, I don't care. And you see now the program detached. But let's now look at corruption.c again. So we had this update name, it did a string copy, and does a string copy into accountsindex.name. Well, that's not ID. Why is that a problem? If we go back to name, you see that name is actually only of length 8. And if we count Alexandria plus a null byte as a string terminator, that's more than 8 characters. Well, it ends up writing beyond the length of this field. And what is the next field? Well, it's ID. And so that string copy ended up overwriting our ID, and we get sad. So this is the kind of stuff that a debugger will easily let you do. And that RR can make even easier because you don't have to know in advance where you need to stop, because you can move backwards. So that's pretty cool. That is RR. Now, you can't always use RR. RR, for example, does not work very well on virtual machines because they require hardware support. They need to be able to monitor certain things in the CPU in order to do the reverse debugging or record the stuff that you need. It's also a Linux-only tool, but when you can use it, it can be extremely powerful. In general, it's really useful for flaky tests. It can be really useful for crashes that are hard to reproduce. Like we talked about in the shell lecture, where you can have this like while loop that runs your tests until it fails. Well, what about you have that while loop, but instead of logging to file, you run RR record. So it will run your tests with RR recording until it fails, and then when it's done, you just type RR replay, and now you have an execution of your tests that you can go backwards and forwards in time as many times as you want to track down the bug. That's pretty cool. The other challenge, of course, with RR and with GDP is that if you modify your program, then you have to exit your session. Right? You have to go out of GDB, out of RR, recompile your program, and then, open up GDB again. And if you open up RR again, the recording is no longer valid because it's a recording of the previous binary, and it can't reuse that recording for a new version of the binary. So this will not help you if you have to modify the code. You would need to re-record or recreate a GDB session. Yep.
If you ever don't have access to RR, is there an easy way in GDB to rerun the program with the same breakpoints without needing to
Yep. Yeah, so you can easily rerun GDB with the same breakpoints from the top. So if I do GDB corruption, let's say I here set a breakpoint for 51, and I do run. Then the program now breaks at 52. And let's say I wanted to execute the next instruction. So I can do next. Next means execute the next instruction. I can do next again. So now we're further down in that file. If I wanted to start from the top again, I type run, and that starts the program from the beginning, but it retains all the same breakpoints. And so this is the way that you would sort of binary search here, right? So we could even do things like I want to watch accounts0.id. I want to run from the beginning, and now it tells me the first time that field is modified, and then I can continue until the next time is modified, and that actually points me at the same bug. Cool. Now, the next thing you might want to do is sometimes the bug is not necessarily like in your code, or you just want to understand what your program is doing. Like, imagine, for example, that you have a program running that just like seems to kind of be stuck, but you don't know what it's stuck on. So you want to introspect what the current process is doing, and you don't necessarily need to care about the code. It's someone else's code. You just want to understand what it's doing, or why it fails, or where all the CPU cycles are going. So then you have this thing called tracing, where you can trace an existing process. And there are a bunch of mechanisms you can use here. One of the most common ones is something called strace. strace lets you trace system calls that a given process is running. So it can either be a process that you start, so you say like strace and then the name of a program, or it can be strace-p and then the process ID of some already running program that strace then attaches to. And let's look at what that looks like. So let's say that I here run strace ls-l. So ls, remember, is the list program. It lists the files in the current directory. -l just means print them one on each line with a little more information about each file. And I want to list all the contents of /temp. Actually, I don't want to. I want to list all the things in this directory. I'm going to here take this is sort of a bash redirect trick to make sure all of the output, whether it's errors or standard out, goes to one place. And then I'll pipe it into less, which is a pager. So instead of this just being dumped into my terminal, it opens a little program that I can scroll up and down in. This is useful if something produces a lot of output. And you'll see what I got was this long sequence of lines that if you squint at them, you'll see that every line starts with the name of a function and open parentheses, and then it's a list of arguments. These are all of the system calls that this program ran. System calls are things that you talk to the operating system, to the kernel to do. So it'll be things like start or stop processes, open files, read files, write to things, access network sockets, and so on. They're not the functions inside of your program. Those will not be logged here. If I zoom out a bunch here, so this is easier to say, you can sort of squint at it and see there is indeed one line per call, but some of them have a lot of arguments. So they're very long lines. But if we go back in here, and we scroll down a little bit, strace. So the things at the top here, if you look at them, you'll see things like LD or exec of the path that is the program. The things at the beginning here are just the things needed to start a process in the first place. It sort of actually tells the operating system to execute this file on disk. It does things like load dependencies it might have on other shared libraries. So the stuff at the beginning is not terribly interesting to us. But if we scroll further down, let's see how far down we need to go. Down here. Oh, this is reading a bunch of, here you can see it actually lists a bunch of time zone files that it opened, because I asked it to do the long printing. That means it needs to print the modification times of the files. That means it needs to have time zone information to look up what that time is in my local time, and therefore it needs to access a bunch of time zone files. And if we go further up, we can see, let's see if I can find read there. Yes, as you can see, there's a lot of stuff in here. It's like hard to really find anything. Well, you can do better than this. So with strace, you can say, I want to only show things that are related to a particular type of operation. So I can, for example, say, I only want things that are related to file operations. So now all the things around, like looking up the, like network operation stuff would not be listed. Loading dynamic libraries would not be listed. And instead, this will now only show things related to files. And in fact, it will also, you can narrow this down to, I only want to show a specific function call, like a specific system call, not all, I said %files, which means anything related to the file system. But I could also say, for example, only redirectory calls. And that's the one I'm trying to find here now. ls does more things than you actually, let's try it without -l, because we don't care too much about that. We can see the output here at the bottom. And okay, fine. We'll do read dir. There's no read dir. I don't know why I don't see this now. Interesting. Oh, I know why. This is because of Nix. I have Nix installed, and so what strace will do is it runs the program you give, and then if that program itself starts other programs, it doesn't trace them. So if you run program A and program A runs program B, then anything program B does is not logged by strace by default. Only things that program A does is logged by default. What you can do, and this is where man pages are useful, you'll see that strace has a bunch of flags, like all the ones we've talked about in the past, and one of the flags that you can pass to strace is follow forks. So you have the -f flag, which says that it also should trace the operations of other commands that get executed. The reason this is related to Nix is that in Nix, ls is actually a Nix program that then invokes the real ls. And so here, if I now switch this to say, I want this to follow forks, and now look for things that are files. Here we go. Then now, let's try, read. Actually, let's do openat maybe. You'll see this line right here. This line is the line that the program uses to open the current directory. So you see here dot, open the current directory, as a directory for then later readdir calls. So in fact, if I now go back and say I want all the file operations, and I search for dot in here, oh, it doesn't count as files. Well, statx. Oh, that's because I removed the -l flag. File. Here we go. Okay, great. So you see the openat dot that we had further up. Now you'll also see that because I passed the -l flag, which tells the program, give me more information about each of the files you listed, it also does a listx attributes and statx for all of the files, all the entries in this directory. Because it now not only wants to list the names, but it also needs to gather that additional information. And so this now tells me that ls is doing more work when I pass -l, because it also needs to do all these stat calls to get additional information about the files. And indeed, if we scroll up, you also see this is more of the time zone information. Here we'll see the statx calls. So list xatters list additional permission bits. Statx is, which it also does for every file, is the thing that gives information about file size, modification time, those kinds of things. So all of these let you trace through exactly what this program is doing when interfacing with the file system. And this can be really useful if you try to, for example, attach to an already executing process with the -p flag. Then this will just start printing reams and reams of information about what that process is actually doing. If it prints nothing, it means that process is just like stuck doing CPU work. It's not actually talking to the operating system at all. And you'll see I passed here -e%file. If we look at the man page for strace, under filtering, you'll see that there are a bunch of other things you can filter for. You can filter for a specific system call, like I did with statx, for example. Or you can say all, which is any system call, which is the default. You can say %file, which is any system call related to file operations, anything related to processes, anything related to networks, anything related to signals, and so on. And so you can sort of craft a list so that the only things that are printed out are the things that you care about. strace is a useful program for this kind of stuff, but it only really does this. It only really does system call tracing. But what about if you actually want to do slightly fancier things? Like, for example, imagine that you want to keep track of you want a latency distribution diagram of how long read calls to the operating system take. strace doesn't let you do that. strace just tells you this function was called with these arguments. So what you really need is like a thing that lets you almost inject programs into the kernel that get to measure what they want. And that thing also exists. It's called eBPF, or Extended Berkeley Packet Filters. These are essentially these little Linux programs that you get to install into the operating system kernel on Linux, and it gets to run with the permissions of the kernel and inspect internal kernel state. You can write like C programs that do this, that have extreme expressive power, but there are also more sort of handy user utilities that let you interact with these. So for example, there's a tool called bpftrace. And bpftrace is kind of like strace, but it uses the eBPF packet filters instead. And it lets you write slightly more advanced expressions. So for example, let me clear the screen here. When you see me clear the screen, by the way, in the terminal, Control L. So if I do echo foo and then Control L, it just clears my screen and goes back to just the terminal at the top. So I can run bpftrace. Let me do a slightly different one maybe to start with. bpftrace. So bpftrace takes a -e flag, which is a packet filtering expression. It is what should get executed and when. These expressions are kind of like awk expressions that we talked about briefly, awk in the first lecture. So they let you filter on the system call, filter on arguments of the system call, and say what should happen for that system call. It's a little bit of a wonky language, but it is pretty flexible. So in this case, I say, I want bpftrace to trace every trace point that is a system call, that is entering that system call of any kind. So sysenter is what the kernel calls any function that is the start of a system call from a program. The star here is like it's like a pattern, so I can match on system calls. So I could here, for example, say statx, and it would match against any system call that is statx. Or I can say star, which is truly any system call. And then I put curly brackets. Oops, that's annoying. bpftrace, come back. And inside the curly brackets, I can put a little BPF program. I can kind of write C in here, but there's also some handy syntax for certain things. So for example, this program will, on every system call, write to a map. That's what that at is a map. Probe is a special word that means the name of the thing you're tracing. So in this case, the name of the system call. Equals count. Count is a function that every time you call it goes up by 1. And so this lets me count the number of invocations of every system call. Now, when I run this program, it just runs. There's no output until I eventually kill the process, and when I kill the process, it'll print out the map of everything it traced. Although it seems to be very unhappy. Why is it unhappy? No, it shouldn't need ls. I think it's because it's gathering a lot of information, because this BPF trace by default will trace your entire kernel. It will not just trace a particular program, it will trace everything that's currently happening on your computer. I've misspelled something. Sys enter probe is count. All right, let's do the other one. That's fine. So this one is a slightly more convoluted BPF trace where I say I want to trace any open@ system call, and I want to print out the COM. COM is the name of the program that is doing the operation. And I want to print out the string argument that is the file name to this thing. So I basically want to print out every file that is opened. And if I run this program, you'll see it attached to probe, and it's now just running, and it's printing anytime any program on my computer is opening any file, prints the name of the program and the name of the path that it opened. You can also limit these. So you could, for example, say here that I only want to trace where com equals tmux, for instance. And this will now only trace calls to open@ where com, so the name of the program, is tmux. In this case, tmux isn't doing much. Is that because I misspelled tmux? Yeah. I have not misspelled tmux. My computer doesn't like me today, it seems. Okay, then we will instead do, this is another handy command, as we can say, I want the process ID to be the current process ID, and then I pass -c and ls. So what this does is -c says run the following command, and set CPID, this is like a special variable, to be equal to the process ID of the thing you just started. And so this lets me only trace the open@ invocations for the program that you ran. So I'll let you see that command line again. It's also in the notes. So here it runs ls, it takes the process ID of ls and sets it to the current process ID. And then our filter for the open@ here is saying PID equals CPID. So the process ID of the process that called this particular system call that you were tracing is equal to that process ID. And so with this, you can start to do really fancy things. And luckily, a lot of other people have built those fancy things for us, so we don't need to build them ourselves. So for example, there is a program called biolatency. It's all written with BPF. It's basically a BPF program that monitors all disk operations, measures how long they took from start to finish, so it monitors the enter and exit of every system call that touches the disk. And then whenever you kill it, it prints out the distribution of times spent accessing the disk. So this is saying that of the system calls that happen to touch my disk, 2 of them took between 4 and 8 microseconds. And 1 of them took between 2 and 4, and so on. The longer you run it, the more data it gathers. There's also one called OpenSnoop, which is basically the program we run earlier, that just snoops on every open call that happens on your computer. So anytime any program opens any file, it prints out what that process was and what it opened. And again, all of this is enabled by the BPF infrastructure, and using this, you can trace programs to do nearly anything, which would be really useful to figure out what a program is doing, why it's stuck, and so on. But there are other kind of things that you could trace. So for example, let's say you wanted to trace your network. Well, you can do TCP dump, which is a program that will dump the traffic that goes over your network interface. So in this case, mine is WLP2S 0 is the name of my Wi-Fi interface because why not? Or you can say any for any interface. And then you can write an expression, a TCP dump expression that says the kinds of internet packets you want to be logged. So for example, I could say anything that goes to port 80. And so now this is going to dump out information about every packet that hits port 80. Well, there are no packets currently hitting port 80, but we can change that. So we can open a new terminal. We can do curl http nevertls.com. Why is it unhappy to do that? So it connected to port 80. It set a request. And now if we go back to TCP dump, you'll see here that a bunch of packets have gone out to the HTTP port. The reason there are a bunch of them is because this logs every packet. It doesn't log the individual request, it just runs every packet that goes over that interface that goes to port 80. So the message that I sent was fairly short, but it was an HTTP request. And so it requires multiple IP packets. And the same thing with the response requires a bunch of IP packets. And what it prints for each one is it prints out the IP address that the traffic went from, the IP address that the traffic went to, the port it went from, the port it went to, IP flags, information about the TCP window, options, the length of the packet, and all such things. And this can be really useful if you're debugging network protocols, because you can make it log whatever information you want about the packets, including their contents. And so that people have written tools on top of this like Wireshark that is a GUI application that you can say, log all the traffic that goes over here, and it understands these different protocols that sit on top of IP. So for example, there's a Wireshark plugin that understands MySQL. And so now you can hook that into your network interface, and it will show you all the MySQL traffic going over it and what the contents of those packets are. And you can write your own plugins for some other protocol you come up with, and it would give you a nice visualization of it and let you debug what's happening to the protocol at the packet level. You can also record packets for replay later on, for example, to do offline testing and so on. So there's a bunch of cool things you could do with this. It will struggle with encrypted traffic, of course, because it logs the raw IP packets, but there are tools like MITM proxy, so man-in-the-middle proxy, which basically pretends to be an HTTPS server and then logs all the packets to disk after decrypting them. There's a bunch of other kinds of debugging too, so not all debugging has to be manual. Sometimes you can get programs to do it for you. One of the most common things that we've seen recently are these things called, recently, it's like the past 20 to 30 years, so maybe not recently, but are these things called sanitizers. Sanitizers are essentially like little extensions to your compiler that make your compiler put extra instructions into the program to do sort of sanity check that your program isn't doing something bad. So as an example, let's look at address sanitizer. Which is one of the most common ones of these. So here I have a program called heap overflow. This particular heap overflow has a similar bug to what we actually observed in the RR example, where I have a buffer that's a certain length, and I try to copy in more bytes that fit into that buffer. This is a very classical bug that you would make in C. Now, when I build this program and run it, heap overflow, and I try to run this program, nothing happens. And the reason nothing happens is because, well, I didn't try to do anything with that memory afterwards. Like, it overwrote some other random part of memory, but I didn't observe that part of memory, so it's like nothing detrimental happened. In reality, like we saw in the RR example, this might have corrupted some other state in my program, but in this particular case, it doesn't cause the program to crash, because nothing depends on the value that was overwritten. But even so, there was a bug in there. We saw that this overwrote more memory than it was supposed to. But luckily, I can compile with this -f sanitize equals address. And this tells the compiler, insert those extra instructions to like sanity check what my program is doing. Now, if I run my program, the program actually crashes. And if I scroll up, you'll see the program says, address sanitizer, find a heap buffer overflow on this address when the program was at this program counter, it's like the instruction it was at. It gives you a backtrace for, like we saw earlier in RR, for these are the functions, like this is the call chain you were at when this problem was caused, and indeed memcopy was the thing that was the problem, that was the thing that was copying over. And it gives you information about where the memory was originally allocated that got overwritten into, and it gives you the contents of the memory and which parts were overwritten and by what. So now you have way more information about the exact nature of the bug that was there. Yep.
It feels like isn't this built into languages like Java and Python, like it automatically throws an error if there's an overflow? Does that mean that like Java and Python have built-in sanitizers?
In a way, so you will find that for some languages, like languages that have stronger runtimes, tend to have more of this checking be done by the runtime. Sometimes it's like off by default because it can be kind of expensive. Also, many of these languages often have ways to bypass it precisely because it can sometimes be expensive. So in Java, for example, you have these like unsafe operations that allow you to do direct memory manipulation, and these can exhibit similar kinds of problems. But I think address sanitizer, for example, I don't think you can use on Java programs. Because they require the Java runtime. They're not native code. Same thing for Python. But many of these have either, like, a lot of it is supported by the language itself, or it ends up being like they have specialized tools that you could use. There are a bunch of other sanitizers too, like the sanitizers that detect concurrency races between different threads in your program and so on. So there's a bunch of these that are useful to familiarize yourself with, especially if you write a lot of native programs, like in C, C++, Objective-C, Rust, and so on. But these require that you recompile your application. You need to compile it with the compiler having these extensions installed. There are also tools that allow you to detect these kinds of problems using a tool that runs your program as it was, like without you needing to rebuild it, which can be useful, for example, if someone else built the program, like it's not yours. There is a tool called Valgrind. Valgrind is a program interpreter. It's an extensible program interpreter. So what it does is it basically pretends to be a CPU. It takes your program and it executes the instructions of that program, but it allows you to, like, because it pretends to be the CPU, it gets to do special things before and after every instruction. This means that it executes a lot more slowly than if you ran your program normally on the CPU, but it also means you can check way more things. So one of the things that's cool about this is Valgrind can actually check every memory operation your program does anywhere without any instrumentation, and tell you this instruction right here wrote to this memory that instruction allocated, and was not supposed to be used here. So it can give you a really, really in-depth analysis of where your bugs are. It can also be used for a lot of other things. Like, for example, it gets used a lot in profiling for giving you instruction level accurate or instruction accurate profiling information. Like, this function takes this many instructions to execute or this many cycles to execute because it gets to actually observe the instructions as they execute. But again, slows down the program a lot. For debugging, I've also found that AI can be an extremely useful tool for a certain subset of debugging. So in particular, anything where there's like cryptic error messages, usually someone else has observed that cryptic error message in a slightly different way, like slightly different memory addresses, slightly different program names. That can sometimes be really annoying to Google for. If you point LLMs at them, they tend to be really good at trying to explain what went wrong and trying to explain workarounds you might be able to use. They can also work really well for programs that have to traverse language boundaries. So imagine you have a Python program that links to a Rust library that in turn uses a C library for something. If you find a weird behavior in your Python program and it's because of a bug in the C program, debugging that yourself can be a real pain sometimes. And LLMs can be very good at this, especially if you give them access to the source code of all three dependencies. You can tell it, I'm observing this behavior in the Python code, and then the LLM will sort of figure out, like, write little reproducers to find a small use case that reproduces that bug, and then it will trace that back to, oh, that's this Rust call. Then it will go to the Rust code and try to reproduce it using just Rust code, and we'll realize, oh, this is actually this C call, and we'll go over to C and write some C programs to reproduce that, and ultimately tells you, like, this part of the C code looks like it's wrong. In general, my experience is that it's not very good at fixing those bugs, but it's very good at finding them for you, and that alone can be a time saver. It can also be really good, like when you get stack traces or crash traces. LLMs can be very good at like helping you navigate through those of like which function was it that you actually cared about. Because these stack traces have been pretty short because these have been example programs. But if you have a stack trace that's like 100 functions deep, it can sometimes be kind of annoying to navigate. And even though they have some structure to them, you can usually do it yourself. LLMs can often help you, especially if it's in an unfamiliar code base to you. I think it's time for us to then move on to profiling, even though it looks like we don't have a lot of time left. Profiling is actually surprisingly related to debugging. A lot of the concepts end up being similar because if you can understand what your code is doing, you can also usually use that to understand how it's performing. First, we need to talk about timing. How do you time how long something takes? Yep. It's all right. So there is a tool that you have access to in basically every shell called time. Time is sort of a built into the shell, and it just is followed by any command that you want to execute. And when you run that program, it will give you this kind of summary. It'll look slightly different on different shells, but ultimately it gives you the same information. It usually gives you 3 numbers. It gives you real, user, and shell. Real is the amount of wall clock time that passed. Like if you looked at a clock from when you hit enter until the end of the output, that's the real time. User is how much time the CPU spent in your code. And then sys is how much CPU time was spent in the kernel executing that program. And the reason I say CPU time here is because if you have many CPUs, and all of them run in parallel, like let's say you have 10 CPUs, then if 1 second passed and all 10 CPUs worked for 1 second, then 10 CPU seconds have passed, even though 1 real-time second has passed. Similarly, in this case, you can see that the actual time it took to execute was 130 milliseconds, but the CPU time was only 54 milliseconds, and the time spent in the kernel was only 9 milliseconds, so where did the rest of the time go? Well, the rest of the time was just spent waiting. In this case, curl lets you access a remote server over HTTP. So I'm trying to fetch the class website. And so a bunch of the time is just spent waiting for the packet to go to the other end of the server on the other end and come back. So wall clock time passes, but no CPU time is spent. This is also one of the simplest ways to profile 2 programs against each other, right? It's just run one with time and run the other with time. And that works, but it's somewhat unreliable. Because usually, if I run this program multiple times, the time is going to vary a little bit between executions. Like this is 124, that's 138. This one spent 20 milliseconds in the kernel. The earlier one spent 9. So what's the truth? Well, there are people who have written tools that help you explore this as well. So for example, there's a tool called Hyperfine. Hyperfine lets you give any number of commands, and it will run all of them multiple times, measure the time they took to execute, and then use some statistical techniques to figure out how, like the standard deviation of the difference in the speed up between the 2 programs. So here, for example, I'm comparing the time it takes to execute the find program against the FD program. The FD program is sort of an improved version of find that has better ergonomics. We talked about it in lecture 1. And here, you see it benchmarked one of them, and then it benchmarked the other, and it gave me some statistics about them. And at the end, it says, find ran 40 times faster than FD. This is a particularly weird case. This is an almost empty directory that, like, FD is not quite optimized for this use case, but it does tell me that FD is not particularly well optimized for this use case. And it gives me some statistical, like, belief that this is true, that it wasn't just the one time I ran it that happened to be true. Sometimes with profiling, even just understanding what your system is doing can be useful. Like, you run a program and it's being slow. Is it being slow because it's using all my CPU cores? Is it being slow because it's only using one of my CPU cores, but to 100%? Is it being slow because my disk is slow? Just monitoring your resource usage can be hugely valuable here. There are a lot of tools you can use for this. HTOP is a good place to start. So HTOP shows you the utilization of your CPU. So in this case, you can see I have 8 cores, and you can see here the CPU utilization of each core. Shows me how much memory is being used. The load average over on the right here is some kind of weird numbers. I recommend you try to look up what they mean. But they're basically how many CPU cores were needed over the past period of time. So what this is telling you is the demand on my CPU is a general 1.2 CPU cores has been needed over the past, I think the first one is like the past 30 seconds or 10 seconds or something. And the next one is like 1 minute or 5 minutes. And the next one is like 20 or 30 minutes. It's like increasingly lengths of time. So you can see how your load has changed over time. And then at the bottom, it shows you a list of all the processes that are currently running on your system. And you can like switch between different views. You can sort them by different columns. You can move through them to see more about the information about what's being shown. You can also switch to other tabs. Like this one shows me the I/O tab here. Shows me how much disk read and write is this process doing, how much network read and write is this doing is also another tab you can get in here. You can sort them by how much they're doing. And so again, you can see where the resource utilization on your system is going, and therefore what your program is probably bottlenecked by. There are a bunch of specialized tools as well. So for example, there's a tool called IOTop that specifically gives you detailed information about input and output, disk or network. There's tools like Free that gives you information about memory usage, LSOF, which gives you information about currently open files, SS, which gives you information about network connections. So like which ports are open, which connections are open, where are they connected to, and so on. There's NetHogs, which gives you information about which things are using the most of your network. There are also other tools that are pretty cool, like btop. btop is like an even better version of htop that shows you lots of stats about your system, including like which disk is using like how much time to spin up, and like all of these detailed statistics and you can like configure it to show exactly the things you care about. So you can go pretty far down this route of introspection on the resource usage of your system. Ultimately though, what you usually want to do is you want to record information about a given program. Like once you really get to the point of, I want to make this program faster, you kind of want to record information about that program. And then you want to try to show where the hottest part of that program is. Like where is that program spending its time looking inside of the code, like inside the functions. And for that, we have a tool called perf. So I'm going to build this program here called slow.c. It's a program that does something slowly. It does some math operations. Now here, if I run slow, then it runs for a little while and eventually it exits. And it computed some results. Who knows what it is, right? I can do perf record -g to say that I want to capture debugging information, and then run the program. When I do this, what perf does is a sampling profiler. So every so often, it will pause the program, check where every CPU is in executing that program, and record that information, and then let it run again. And it does this many, many times a second to give you a sample of where in your program is the CPU spending the most time. When it's done, you can run perf report. What perf report does is give you this kind of view. So it says 100% of my time was spent in or under start. The first column here, children, is this function and its child functions, like anything it called. So obviously start is the start of my binary. All the time is spent under the start of my binary. But the second column is how much time was spent in this function specifically, not in its descendants. So you'll see here, here's my main function. I can press plus to expand it. And I can see that 43.6% was spent in computing cosine, and 43.2% or 3% was spent in computing sine. You can also here get annotated information around where like showing you listings of code as well to annotate to this function. Here I'm annotating it with just the raw assembly. There are also ways here where you can, if you press H, you get help information, and so you can ask it to show you line numbers. You can also ask it to show additional information like source code lines, although now my terminal isn't tall enough, so it gets sad. There's a bunch of things you can use this to sort of dig into your program. And in fact, if I go to main here, I can annotate main. Oh, why does it not give me my toggle source code view? S. Oh, I don't think it. Oh yeah, here. It's just I was just blind. So you'll see here that this for loop is this instruction. You kind of have to squint to disambiguate the assembly instructions on the C code. But you see they get interspersed here so that you can see this line of code is these lines of assembly code. And each of these assembly instructions took this much time into the percentage of overall compute time. And so this lets you get sort of really drilled down on like this part of this line of my code is where the CPU spends the most time. This can be hard to parse, though. Humans are not very good at parsing this kind of information, especially not at scale. And so people have built better tools for visualizing these things. For example, there's a tool called FlameGraph that here I'm using Inferno, which is a Rust port of FlameGraph, just because it's what I happen to have installed. But it allows you to take the output of perf, in this case perf script, parse it through a couple of scripts, and what it produces is an SVG file. And if I open this SVG file, it gives me this kind of view. So you'll see at the bottom is sort of the entry point to my binary, and then you'll see going up a little bit that my main function is here, and then you'll see that in the main function, the width of the bar indicates how much time was spent there. And you can see here, about half the time of main was spent in cosine, and about half the time of main was spent in sine. If you get really complex programs, this will end up looking like this giant bar of flames because it colors things in that way. And you can see like the wider flames are where you spend more time. There's an example of this in the lecture notes as well for a more complicated program. If you open these in your browser, they're even clickable. So you can click to zoom, expand information about the different frames and so on. Extremely useful for figuring out where your program is spending its time. As I mentioned, though, this is a sampling profiler. So it only gets to see where your CPU is when it interrupts the program, when it pauses the program. And that means you get imperfect information. You can increase the frequency at which it samples the program, but then you're also slowing the program down because it has to pause more often. If you want like really, really accurate information about where the program is spending its time, you can run it through Valgrind. So Valgrind, as I mentioned, interprets every single assembly instruction as though it were the CPU. That's mostly true, at least. And so it gets to truly measure, it doesn't sample, it actually traces the program, gets to measure how often every single assembly instruction is called, but as a result, it also tends to be quite slow. So Valgrind has a bunch of these different modes where you can count different things like, did you use your memory correctly? Or how many times is each assembly instruction called? So it has these extensions, these plugins for measuring different things that might be useful. It's a very versatile tool in that sense. Now, the last thing I want to mention here is that profiling is not just about being able to evaluate the runtime performance of your program, like how quickly different parts run. It is also about looking at the output of your program and trying to understand why that output behaves in a certain way. Sometimes it's also about why does your program's behavior change in a certain way in response to changes to the input. So for example, imagine you have a program that searches for strings and files, kind of like the grep tool. You might want to understand how your program slows up or speeds down in relation to the size of the input and the size of the pattern. Or maybe the complexity of the pattern, but let's say size, like length of the pattern. For this, you want to visualize the data. Realistically, if you end up with a giant text file of all the sort of, I ran it with this input size and this pattern size and it took this many microseconds, that long list, like that long Excel spreadsheet is not going to be particularly useful to you. So instead, you usually want to use some kind of visualization to plot that information. In the terminal, we have a bunch of tools that are really helpful for doing this kind of easy plotting. For example, there's a tool called GNUplot. GNUplot is built for the shell. So in GNUplot, you write these little expressions similar to what we've seen now with a bunch of these programs, like for bpftrace, remember there's like -e, and you get to write a little program in a specialized language. GNUplot is a similar program where you can pass -e, and you have a little plotting language. You can say, plot this column of the input, like from standard in, against this column of the input, so x and y, and then it plots you an image that's x against y. And you can change the colors, you can plot multiple things, you can change the axes and so on. This is a very useful tool for just like quick and dirty plotting. There are also more extensive tools if you want to do deeper analysis, you want to do many plots, you want to do fancier things with the plots or post-processing of the data, where you can either use matplotlib in Python. So you write a little Python program that reads the input of whatever kind it might be and then plots it. Or in R, there is a plotting library called ggplot2 that I personally find extremely useful, in part because it has this feature called facet wrapping. So facet wrapping allows you to say, you know, I have my input, I have things that are going to be the x and y, but then I also want to say, create one graph where, like let's say my x-axis is the size of the input, and my y-axis is the time it took to execute the program for something like grep. Well, what if I want to see how the complexity of the pattern changes how long this takes? So not the length, but the complexity. Well, the length might be different lines on one plot, but then I want one plot per complexity. And I want them all to show next to each other so I can compare them. Facet wrapping is a thing in ggplot where you can say, I want to plot where the color is dictated by this column, x is dictated by this column, y is indicated by this column, and which graph is indicated by this column. And so it'll automatically generate a set of graphs for you. And it can even then create grids of graphs so that you have like a XY coordinate system that is the graphs, so that some other column increases across graphs and increases across graphs in this direction. You can plot like 8-dimensional data sets or something. Not 8-dimensional. 5-dimensional data sets in something that you can actually visually recognize. And this is one of the superpowers of profiling, is not just to be able to extract information about how your program behaves, but also to be able to visualize that information so that you can identify problems or weird patterns and do something about them. The thing I'll end on here is when you know that you will want to do profiling, you often go back into your program and go, oh, I need to log all this information, like how big the size of the input was, or how long this particular function took, or I want to plot, some internal information about the size of a graph or something. Usually, this is the kind of stuff that if you take the time to think through what to log early on, this gets all the back to the start of the lecture, think when you log information about both how you log and what you log. The more you can do structured logging so that it's easy to parse out later, for example, for plotting, and the more you can proactively think about what information to log, like the sizes of things, then when you later want to profile your program, you already have all the information in the logs to then plot all these interesting graphs that will point you at potential problems or potential scaling cliffs in your program as you modify their behavior. Cool. There's a bunch more details in the lecture notes here about debugging and profiling, including some additional tools, some additional techniques, and also some of the nuances that are involved here. So highly recommend you go through them. There are also exercises as always. That's all. We're a little bit over time, but if you have questions, I'm happy to take them. Cool.
Thank you.
Thank you.